NVIDIA is the perfect company to do that. Gosh, that's our destiny. Use AI to recreate AI. The technology that we showed you there is very similar to the technology that you're enjoying to take you to a digital twin we call NVIDIA. All right, let's talk about data centers. That's not bad, huh? Gaussian splats, just in case. Gaussian splats. Well, let's talk about data centers. Blackwell is in full production, and this is what it looks like. It's an incredible, you know, for people, for us, this is a sight of beauty. Would you agree? This is, how is this not beautiful? How is this not beautiful? Well, this is a big deal because we made a fundamental transition in computer architecture. I just want you to know that, in fact, I've shown you a version of this about 3 years ago. It was called Grace Hopper, and the system was called Ranger. The Ranger system is about maybe about half of the width of the screen. And it was the world's first NVLink 32. 3 years ago, we showed Ranger working, and it was way too large, but it was exactly the right idea. We were trying to solve scale up. Distributed computing is about using a whole lot of different computers working together to solve a very large problem. But there's no replacement for scaling up before you scale out. Both are important, but you want to scale up first before you scale out. While scaling up is incredibly hard, there is no simple answer for it. You're not going to scale it up, you're not going to scale it out like Hadoop. Take a whole bunch of commodity computers, hook it up into a large network, and do in-storage computing using Hadoop. Hadoop was a revolutionary idea, as we know. It enabled hyperscale data centers to solve problems of gigantic sizes and using off-the-shelf computers. However, the problem we're trying to solve is so complex that scaling in that way would have simply cost way too much power, way too much energy. It would have never, deep learning would have never happened. And so the thing that we had to do was scale up first. Well, this is the way we scaled up. I'm not going to lift this. This is 70 pounds. This is the last generation system architecture. Is called HGX. This revolutionized computing as we know it. This revolutionized artificial intelligence. This is 8 GPUs. 8 GPUs. Each one of them is kind of like this. Okay. This is 2 GPUs, 2 Blackwell GPUs in one Blackwell package. 2 Blackwell GPUs in one Blackwell package. And there are 8 of these underneath this. Okay? And this connects into what we call NVLink 8. This then connects to a CPU shelf like that. So there's dual CPUs, and that sits on top. And we connect it over PCI Express, and then many of these get connected with InfiniBand, which turns into what is an AI supercomputer. This is the way it was in the past. This is how we started. Well, this is as far as we scaled up before we scaled out. But we wanted to scale up even further. And I told you that Ranger took this system and scaled it up by another factor of 4. And so we had NVLink 32, but the system was way too large. And so we had to do something quite remarkable, re-engineer how NVLink worked and how scale-up worked. And so the first thing that we did was we said, listen, the NVLink switches are in this system embedded on the motherboard. We need to disaggregate the NVLink system and take it out. So this is the NVLink system. Okay, this is an NVLink switch. This is the highest performance switch the world's ever made. And this makes it possible for every GPU to talk to every GPU at exactly the same time at full bandwidth. Okay, so this is the NVLink switch. We disaggregated it, we took it out, and we put it in the center of the chassis. So there are 18 of these switches in 9 different racks, 9 different switch trays, we call them. And then the switches are disaggregated. The compute is now sitting in here. This is equivalent to these 2 things in compute. What's amazing is this is completely liquid cooled. And by liquid cooling it, we can compress all of these compute nodes into one rack. This is the big change of the entire industry. All of you in the audience, I know how many of you are here. I want to thank you for making this fundamental shift from integrated NVLink to disaggregated NVLink, from air-cooled to liquid-cooled, from 60,000 components per computer or so to 600,000 components per rack, 120 kilowatts, fully liquid cooled, and as a result, we have a 1 exaflops computer in one rack. Isn't it incredible? So this is the compute node. This is the compute node, okay? And that now fits in one of these. Now 3,000 pounds, 5,000 cables, about 2 miles worth. Just an incredible electronics. 600,000 parts, I think that's like 20 cars. 20 cars worth of parts, and integrates into one supercomputer. Well, our goal is to do this. Our goal is to do scale up, and this is what it now looks like. We essentially wanted to build this chip. It's just that no reticle limits can do this, no process technology can do this. It's 130 trillion transistors, 20 trillion of it is used for computing. So it's not like you can't reasonably build this anytime soon. And so the way to solve this problem is to disaggregate it, as I've described, into the Grace Blackwell NVLink 72 rack. But as a result, we have done the ultimate scale up. This is the most extreme scale up the world has ever done. The amount of computation that's possible here, the memory bandwidth, 570 terabytes per second. Everything in this machine is now in T's. Everything's a trillion. And you have an exaflops, which is 1,000,000 trillion floating point operations per second. Well, the reason why we wanted to do this is to solve an extreme problem. And that extreme problem, a lot of people misunderstood to be easy. And in fact, it is the ultimate extreme computing problem, and it's called inference. And the reason for that is very simple. Inference is token generation by a factory, and a factory is revenue and profit generating, or lack of. And so this factory has to be built with extreme efficiency, with extreme performance, because everything about this factory directly affects your quality of service, your revenues, and your profitability. Let me show you how to read this chart, because I want to come back to this a few more times. Basically, you have 2 axes. On the x-axis is the tokens per second. Whenever you put a prompt into ChatGPT, what comes out is tokens. Those tokens are reformulated into words. You know, it's more than a token per word, okay? and they'll tokenize things like THE could be used for the, it could be used for them, it could be used for theory, it could be used for theatrics, it could be used for all kinds of, okay? And so THE is an example of a token. They reformulate these tokens to turn into words. Well, we've already established that if you want your AI to be smarter, you want to generate a whole bunch of tokens. Those tokens are reasoning tokens, consistency checking tokens, coming up with a whole bunch of ideas so they can select the best of those ideas tokens. And so those tokens, it might be second guessing itself. It might be, is this the best work you could do? And so it talks to itself just like we talk to ourselves. And so the more tokens you generate, the smarter your AI. But if you take too long to answer a question, the customer's not going to come back. This is no different than web search. There is a real limit to how long it can take before it comes back with a smart answer. And so you have these two dimensions that you're fighting against. You're trying to generate a whole bunch of tokens, but you're trying to do it as quickly as possible. Therefore, your token rate matters. So you want your tokens per second for that one user to be as fast as possible. However, in computer sciences and factories, there's a fundamental tension between latency response time and throughput. And the reason is very simple. If you're in the large, high-volume business, you batch up, it's called batching, you batch up a lot of customer demand, and you manufacture a certain version of it for everybody to consume later. However, from the moment that they batched up and manufacture whatever they did, to the time that you consumed it, could take a long time. So no different for computer science, no different for AI factories that are generating tokens. And so you have these two fundamental tensions. On the one hand, you would like the customer's quality of service to be as good as possible, smart AIs that are super fast. On the other hand, you're trying to get your data center to produce tokens for as many people as possible so you can maximize your revenues. The perfect answer is to the upper right. Ideally, the shape of that curve is a square that you could generate very fast tokens per person up until the limits of the factory, but no factory can do that. And so it's probably some curve, and your goal is to maximize the area under the curve, okay, the product of X and Y, and the further you push out, more likely it means the better of a factory that you're building. Well, it turns out that in tokens per second for the whole factory and tokens per second response time, one of them requires enormous amount of computation, flops, and then the other dimension requires an enormous amount of bandwidth and flops. And so this is a very difficult problem to solve. The good answer is that you should have lots of flops and lots of bandwidth and lots of memory and lots of everything. That's the best answer to start, which is the reason why this is such a great computer. You start with the most flops you can, the most memory you can, the most bandwidth you can, of course, the best architecture you can, the most energy efficiency you can, and you have to have a programming model that allows you to run software across all of this insanely hard so that you could do this. Now let's just take a look at this one demo to give you a tactile feeling of what I'm talking about. Please play it.
Traditional LLMs capture foundational knowledge, while reasoning models help solve complex problems with thinking tokens. Here, a prompt asks to seat people around a wedding table while adhering to constraints like traditions, photogenic angles, and feuding family members. Traditional LLM answers quickly with under 500 tokens. It makes mistakes in seating the guests, while the reasoning model thinks with over 8,000 tokens to come up with the correct answer. It takes a pastor to keep the peace.
Okay, as all of you know, if you have a wedding party of 300 and you're trying to find the optimal seating for everyone, That's a problem that only AI can solve or a mother-in-law can solve. And so that's one of those problems that co-op cannot solve. Okay, so what you see here is that we gave it a problem that requires reasoning, and you saw R1 goes off and it reasons about it, tries all these different scenarios, and it comes back and it tests its own answer. It asks itself whether it did it right. Meanwhile, the last generation language model does a one-shot. So the one-shot is 439 tokens. It was fast, it was effective, but it was wrong. So it was 439 wasted tokens. On the other hand, in order for you to reason about this problem, and this is just that was actually a very simple problem. You know, you just give it a few more difficult variables, and it becomes very difficult to reason through. And it took 8,000, almost 9,000 tokens. And it took a lot more computation because the model's more complex. Okay, so that's one dimension. Before I show you some results, let me explain something else. So the answer, if you look at Blackwell, you look at the Blackwell system, and it's now the scaled up NVLink 72. The first thing that we have to do is we have to take this model, and this model is not small. It's, you know, in the case of R1, people think R1 is small, but it's 680 billion parameters. Next generation models could be trillions of parameters. And the way that you solve that problem is you take these trillions and trillions of parameters and this model, and you distribute the workload across the whole system of GPUs. You can use tensor parallel. You can take one layer of the model and run it across multiple GPUs. You could take a slice of the pipeline and call that pipeline parallel and put that on multiple GPUs. You could take different experts and put it across different GPUs. We'll call it expert parallel. The combination of pipeline parallelism and tensor parallelism and expert parallelism, the number of combinations is insane. And depending on the model, depending on the workload, depending on the circumstance, how you configure that computer has to change so that you can get the maximum throughput out of it. You also sometimes optimize for very low latency, sometimes you try to optimize for throughput, and so you have to do some in-flight batching. A lot of different techniques for batching and aggregating work. And so the software, the operating system for these AI factories is insanely complicated. Well, one of the observations, and this is a really terrific thing about having a homogeneous architecture like NVLink 72, is that every single GPU could do all the things that I just described. And we observe that these reasoning models are doing a couple of phases of computing. One of the phases of computing is thinking. When you're thinking, you're not producing a lot of tokens. You're producing tokens that you're maybe consuming yourself. You're thinking. Maybe you're reading. You're digesting information. That information could be a PDF. That information could be a website. You could literally be watching a video, ingesting all of that at super linear rates. And you take all of that information and you then formulate the answer, formulate a plan to answer. And so that digestion of information, context processing, is very flops intensive. On the other hand, during the next phase is called decode. So the first part we call prefill. The next phase of decode requires floating point operations, but it requires an enormous amount of bandwidth. And it's fairly easy to calculate. You know, if you have a model and it's a few trillion parameters, well, it takes a few terabytes per second. Notice I was mentioning 576 terabytes per second. It takes terabytes per second to just pull the model in from HBM memory and to generate literally one token. And the reason it generates one token is because, remember, that these large language models are predicting the next token. That's why they say the next token. It's not predicting every single token, it's predicting the next token. Now we have all kinds of new techniques, speculative decoding, and all kinds of new techniques for doing that faster, but in the final analysis, you're predicting the next token, okay? And so you ingest, pull in the entire model and the context, we call it a KV cache, and then we produce one token. And then we take that one token, we put it back into our brain, we produce the next token. Every single time we do that, we take trillions of parameters in, we produce one token. Trillions of parameters in, produce another token. Trillions of parameters in, produce another token. And notice that demo, we produced 8,600 tokens. So trillions of bytes of information have been taken into our GPUs and produced one token at a time, which is fundamentally the reason why you want NVLink. NVLink gives us the ability to take all of those GPUs and turn them into one massive GPU, the ultimate scale up. And the second thing is that now that everything is on NVLink, I can disaggregate the prefill from the decode, and I could decide I want to use more GPUs for prefill, less for decode, because I'm thinking a lot. It's agentic. I'm reading a lot of information. I'm doing deep research. Notice during deep research, and earlier I was listening to Michael, and Michael was talking about him doing research, and I do the same thing. And we go off and we write these really long research projects for our AI, and I love doing that because I already paid for it. And I just love making our GPUs work. And nothing gives me more joy. So I write up, and then it goes off and it does all this research, and it went off to like 94 different websites, and it read all this, and I'm reading all this information, and it formulates an answer and writes the report. It's incredible, okay? During that entire time, prefill is super busy, and it's not really generating that many tokens. On the other hand, when you're chatting with the chatbot, and millions of us are doing the same thing, it is very token generation heavy. It's very decode heavy, okay? And so depending on the workload, we might decide to put more GPUs into decode, depending on the workload, put more GPUs into prefill. Well, this dynamic operation is really complicated. So I've just now described pipeline parallel, tensor parallel, expert parallel, in-flight batching, disaggregated inferencing, workload management, and then I've got to take this thing called a KV cache, I've got to route it to the right GPU, I've got to manage it through all the memory hierarchies. That piece of software is insanely complicated. And so today we're announcing the NVIDIA Dynamo. NVIDIA Dynamo does all that. It is essentially the operating system of an AI factory. Whereas in the past, in the way that we ran data centers, our operating system would be something like VMware. And we would orchestrate, and we still do, we're a big user, we orchestrate a whole bunch of different enterprise applications running on top of our enterprise IT. But in the future, the application is not enterprise IT, it's agents. And the operating system is not something like VMware, it's something like Dynamo. And this operating system is running on top of not a data center, but on top of an AI factory. Now we call it Dynamo for a good reason. As you know, the Dynamo was the first instrument that started the last industrial revolution, the industrial revolution of energy. Water comes in, electricity comes out. It's pretty fantastic. Water comes in, you light it on fire, turn it to steam, and what comes out is this invisible thing that's incredibly valuable. It took another 80 years to go to alternating current, but Dynamo is where it all started. Okay, so we decided to call this operating system, this piece of software, insanely complicated software, the NVIDIA Dynamo. It's open source, and we're so happy that so many of our partners are working with us on it. And one of my favorite partners, I just love them so much because of the revolutionary work that they do, and also because Aravin's such a great guy. But Perplexity is a great partner of ours in working through this. Okay, so anyhow, really, really great. Okay, so now we're going to have to wait until we scale up all these infrastructure, but in the meantime, we've done a whole bunch of very in-depth simulation. We have supercomputers doing simulation of our supercomputers, which makes sense. And I'm now going to show you the benefit of everything that I've just said. And remember the factory diagram. On the x-axis is tokens per second throughput, on the y-axis, tokens per second throughput of the factory, and the x-axis, tokens per second of the user experience. And you want super smart AIs, and you want to produce a whole bunch of it. This is Hopper. Okay, so this is Hopper, and it can produce for one user, for each user, about 100 tokens per second. This is 8 GPUs, and it's connected with InfiniBand, and I'm normalizing it to tokens per second per megawatt. So it's a 1 megawatt data center, which is not a very large AI factory, but anyhow, 1 megawatt, okay? And so it can produce for each user 100 tokens per second, and it can produce at this level, whatever that happens to be, 100,000 tokens per second for that 1 megawatt data center. Or it can produce about 2.5 million tokens per second, 2.5 million tokens per second for that AI factory if it was super batched up and the customer is willing to wait a very long time. Okay, does that make sense? All right, so nod. All right, because this is where, every GTC, there's the price for entry, you guys know, and it's like you get tortured with math, okay? This is the only at NVIDIA do you get tortured with math. All right, so Hopper, you get 2.5. Now, what's that 2.5 million? How do you translate that? 2.5 million, remember, ChatGPT is like $10 per million tokens, right? $10 per million tokens. Let's pretend for a second that's, I think the $10 per million tokens is probably down here, okay? I'd probably say it's down here, but let me pretend it's up there, because 2.5 million, 10, so $25 million per second. Does that make sense? That's how you think through it. Or on the other hand, if it's way down here, then the question is, so it's 100,000, just divide that by 10, okay? $250,000 per factory per second. And then, it's 30 million seconds in a year, and that translates into revenues for that 1 megawatt data center. And so that's your goal. On the one hand, you would like your token rate to be as fast as possible so that you can make really smart AIs. And if you have smart AIs, people pay you more money for it. On the other hand, the smarter the AI, the less you can make in volume. Very sensible trade-off. And this is the curve we're trying to bend. Now, what I'm just showing you right now is the fastest computer in the world, Hopper. It's the computer that revolutionized everything. And so how do we make that better? So the first thing that we do is we come up with Blackwell with NVLink 8. Same Blackwell, that one same compute, and that one compute node with NVLink 8 using FP8. And so Blackwell is just faster, bigger, more transistors, more everything. But we like to do more than that, and so we introduce a new precision. It's not quite as simple as 4-bit floating point, but using 4-bit floating point, we can quantize the model, use less energy to do the same. And as a result, when you use less energy to do the same, you could do more. Because remember, one big idea is that every single data center in the future will be power limited. Your revenues are power limited. You could figure out what your revenues are going to be based on the power you have to work with. This is no different than, like many other industries. And so we are now a power limited industry. Our revenues will associate with that. Well, based on that, you want to make sure you have the most energy efficient compute architecture you can possibly get. Then we scale up with NVLink 72. Does that make sense? Look at the difference between that, NVLink 72 FP4, and then, because our architecture is so tightly integrated, and now we add Dynamo to it, Dynamo can extend that even further. Are you following me? So Dynamo also helps Hopper, but Dynamo helps Blackwell incredibly. Now, yep. Only at GTC do you get an applause for that. And so now notice what I put, those two shiny parts, that's kind of where your max Q is. You know, that's likely where you'll run your factory operations. You're trying to find that balance between maximum throughput and maximum quality of AI. Smartest AI, the most of it. Those two, that XY intercept is really what you're optimizing for. And that's what it looks like if you look underneath those two squares. Blackwell is way, way better than Hopper. And remember, this is not ISO chips. This is ISO power. This is ultimate Moore's Law. This is what Moore's Law was always about in the past. And now here we are, 25x in one generation as ISO power. This is not ISO chips, it's not ISO transistors, it's not ISO anything. ISO power, the ultimate limiter. There's only so much energy we can get into a data center. And so within ISO power, Blackwell is 25 times. Now here's that rainbow. That's incredible. That's the fun part. Look, all the different underneath the Pareto, the frontier Pareto, we call it the frontier Pareto, under the frontier Pareto are millions of points we could have configured the data center to do. We could have parallelized and split the work and sharded the work in a whole lot of different ways. And we found the most optimal answer, which is the Pareto, the frontier Pareto, okay, the Pareto frontier. And each one of them, because of the color, shows you it's a different configuration. Which is the reason why this image says very, very clearly you want a programmable architecture that is as homogeneously fungible as possible, because the workload changes so dramatically across the entire frontier. And look, we got on the top, expert parallel 8, batch of 3000, disaggregation off, dynamo off. In the middle, expert parallel 64 with the 26% is used for context, so dynamo is turned on, 26% context, the other 74% is not. Batch of 64, and expert parallel of 64 on one, expert parallel of 4 on the other. And then down here, all the way to the bottom, you got tensor parallel 16 with expert parallel 4, batch of 2, 1% context. The configuration of the computer is changing across that entire spectrum. And then this is what happens. So this is with input sequence length. This is a kind of a commodity test case. This is a test case that you can benchmark relatively easily. The input is 1,000 tokens. The output is 2,000. Notice earlier, we just showed you a demo where the output is very simply 9,000, right? 8,000, okay? And so obviously this is not representative of just that one chat. Now this one is more representative, and this is what, the goal is to build these next generation computers for next generation workloads. And so here's an example of a reasoning model. And in a reasoning model, Blackwell is 40 times the performance of Hopper, straight up. Pretty amazing. I've said before, somebody actually asked, why would I say that? But I said before that when Blackwell starts shipping in volume, you couldn't give Hoppers away. And this is what I mean. And this makes sense. If you're still looking to buy a Hopper, don't be afraid. It's okay. But I'm the chief revenue destroyer. My sales guys are going, oh no, don't say that. There are circumstances where Hopper is fine. That's the best thing I could say about Hopper. There are circumstances where you're fine. Not many. If I had to take a swing. And so that's kind of my point. When the technology is moving this fast, and because the workload is so intense and you're building these things, they're factories, we really like you to invest in the right versions. Okay, just to put it in perspective, this is what a 100 megawatt factory looks like. This is a 100 megawatt factory. You have, based on Hoppers, you have 45,000 dies, 1,400 racks, and it produces 300 million tokens per second, okay? And then this is what it looks like with Blackwell. You have 86, yeah, I know. That doesn't make any sense. Okay, so we're not trying to sell you less. Okay, our sales guys are going, Jensen, you're selling them less. This is better. Okay, and so anyways, the more you buy, the more you save. It's even better than that. Now the more you buy, the more you make, you know? And so anyhow, remember, everything is in the context, everything is now in the context of AI factories. And although we talk about the chips, you always start from scale up. We talk about the chips, but you always start from scale up, the full scale up. What can you scale up to the maximum? I want to show you now what an AI factory looks like, but AI factories are so complicated. I just gave you an example of one rack. It has 600,000 parts. You know, it's 3,000 pounds. Now, you've got to take that and connect it with a whole bunch of others. And so we are starting to build what we call the digital twin of every data center. Before you build a data center, you have to build a digital twin. Let's take a look at this. This is just incredibly beautiful. The world is racing to build state-of-the-art, large-scale AI factories. Bringing up an AI gigafactory is an extraordinary feat of engineering, requiring tens of thousands of workers, from suppliers, architects, contractors, and engineers, to build, ship, and assemble nearly 5 billion components and over 200,000 miles of fiber, nearly the distance from the Earth to the Moon. The NVIDIA Omniverse blueprint for AI factory digital twins enables us to design and optimize these AI factories long before physical construction starts. Here, NVIDIA engineers use the blueprint to plan a 1 gigawatt AI factory, integrating 3D and layout data of the latest NVIDIA DGX SuperPods and advanced power and cooling systems from Vertiv and Schneider Electric, and optimized topology from NVIDIA Air, a framework for simulating network logic, layout, and protocols. This work is traditionally done in silos. The Omniverse blueprint lets our engineering teams work in parallel and collaboratively, letting us explore various configurations to maximizing TCO and power usage effectiveness. NVIDIA uses Cadence Reality Digital Twin, accelerated by CUDA and Omniverse libraries, to simulate air and liquid cooling systems. And Schneider Electric with ETAP, an application to simulate power block efficiency and reliability. Real-time simulation lets us iterate and run large-scale what-if scenarios in seconds versus hours. We use the digital twin to communicate instructions to the large body of teams and suppliers, reducing execution errors and accelerating time to bring up. And when planning for retrofits or upgrades, we can easily test and simulate cost and downtime, ensuring a future-proof AI factory. This is the first time anybody who builds data centers says, oh, that's so beautiful. All right, I got a race here because turns out I got a lot to tell you. And so if I go a little too fast, it's not because I don't care about you, it's just I got a lot of information to go through. All right, so first, our roadmap. We're now in full production of Blackwell. Computer companies all over the world are ramping these incredible machines at scale. And I'm just so pleased and so grateful that all of you worked hard on transitioning into this new architecture. And now, in the second half of this year, we'll easily transition into the upgrade. So we have the Blackwell Ultra NVLink 72. It's 1.5 times more flops. It's got a new instruction for attention. It's 1.5 times more memory. All that memory is useful for things like KV cache. It's 2 times more bandwidth, okay, for networking bandwidth. And so now that we have the same architecture, we'll just kind of gracefully glide into that, and that's called Blackwell Ultra, okay? So that's coming second half of this year. Now, there's a reason why this is the only product announcement in any company where everybody's going, yeah, next. Yeah. And in fact, that's exactly the response I was hoping to get. And here's why. Look, we're building AI factories and AI infrastructure. It's going to take years of planning. This isn't like buying a laptop. This isn't discretionary spend. This is spend that we have to go plan on. And so we have to plan on having, of course, the land and the power, and we have to get our CapEx ready, and we get engineering teams, and we have to lay it out a couple, 2, 3 years in advance, which is the reason why I show you our roadmap a couple, 2, 3 years in advance, so that we don't surprise you in May. Hi, in another month we're going to go to this incredible new system. I'll show you an example in a second. And so we plan this out in multiple years. The next click, 1 year out, is named after an astronomer, and her grandkids are here. Her name is Vera Rubin. She discovered dark matter. Okay, yep. Vera Rubin is incredible because the CPU is new. It's twice the performance of Grace, and more memory, more bandwidth, and yet just a little tiny 50-watt CPU is really quite incredible. Okay, and Rubin, brand new GPU, CX9, brand new networking smart NIC, NVLink 6, brand new NVLink, brand new memories, HBM4. Basically, everything is brand new except for the chassis. And this way, we could take a whole lot of risk in one direction and not risk a whole bunch of other things related to the infrastructure. And so Vera Rubin, NVLink 144, is the second half of next year. Now, one of the things that I made a mistake on, and so I just need you to make this pivot. We're going to do this one time. Blackwell is really 2 GPUs in one Blackwell chip. We call that one chip a GPU, and that was wrong. And the reason for that is it screws up all the NVLink nomenclature and things like that. So going forward, without going back to Blackwell to fix it, going forward, when I say NVLink 144, it just means that it's connected to 144 GPUs. And each one of those GPUs is a GPU die, and it could be assembled in some package. How it's assembled could change from time to time, okay? And so each GPU die is a GPU. Each NVLink is connected to the GPU. And so Vera Rubin, NVLink 144. And then this now sets the stage for the second half of the year, the following year, we call Rubin Ultra. Okay, so Vera Rubin Ultra. I know. This where you go, all right, so this is Vera Rubin Ultra, second half of 27. It's NVLink 576, extreme scale up. Each rack is 600 kilowatts, 2.5 million parts, okay? And obviously a whole lot of GPUs. And everything is X factor more. So 14 times more flops, 15 exaflops. Instead of 1 exaflop, as I mentioned earlier, is now 15 exaflops, scaled up exaflops, okay? And it's 4.6 petabytes, so 4,600 terabytes per second scale up bandwidth. I don't mean aggregate, I mean scale up bandwidth. And of course, a brand new NVLink switch and CX9, okay? And so notice 16 sites, 4 GPUs in one package, extremely large NVLink. Now just put that in perspective, this is what it looks like, okay? Now this is gonna be fun. So you are just literally ramping up Grace Blackwell at the moment, and I don't mean to make it look like a laptop, but here we go. Okay, so this is what Grace Blackwell looks like, and this is what Rubin looks like. ISO dimension. And so this is another way of saying, before you scale out, you have to scale up. Does that make sense? Before you scale out, you scale up. And then after that, you scale out with amazing technology that I'll show you in just a second. All right, so first you scale up, and then now that gives you a sense of the pace at which we're moving. This is the amount of scale up flops. This is scale up flops. Hopper is 1x, Blackwell is 68x, Rubin is 900x. Scale up flops. And then if I turn it into essentially your TCO, which is power on top, power per, and the underneath is the area underneath the curve that I was talking to you about, the square underneath the curve, which is basically flops times bandwidth, okay? So the way you think about a very easy gut check on whether your AI factories are making progress is watts divided by those numbers. And you can see that Rubin is going to drive the cost down tremendously. Okay, so that's very quickly NVIDIA's roadmap. Once a year like clock ticks, once a year. Okay, how do we scale up? Well, we were preparing to scale out. That was scale up, was NVLink. Our scale out network is InfiniBand and Spectrum-X. Most were quite surprised that we came into the Ethernet world. And the reason why we decided to do Ethernet is if we could help Ethernet become like InfiniBand, have the qualities of InfiniBand, then the network itself would be a lot easier for everybody to use and manage. And so we decided to invest in Spectrum. We call it Spectrum-X, and we brought to it the properties of congestion control and very low latency and amount of software that's part of our computing fabric. And as a result, we made Spectrum-X incredibly high performant. We scaled up the largest single GPU cluster ever as one giant cluster with Spectrum-X, right? And that was Colossus. And so there are many other examples of it. Spectrum-X is unquestionably a huge home run for us. One of the areas that I'm very excited about is Spectrum-X is not just for AI clouds, but Spectrum-X also makes it possible for us to help every enterprise become an AI company. And so, was it last week or the week before, Chuck Robbins and Cisco and NVIDIA announced a partnership for Cisco, the world's largest enterprise networking company, to take Spectrum-X and integrate it into their product line so that they could help the world's enterprises become AI companies. We're at 100,000 with CX8, CX7. Now CX8's coming, CX9's coming. And during Rubin's time frame, we would like to scale out the number of GPUs to many hundreds of thousands. Now, the challenge with scaling out GPUs to many hundreds of thousands is the connection of the scale out. This connection on scale up is copper. We should use copper as far as we can, and that's, call it a meter or two. And that's incredibly good connectivity, very high reliability, very good energy efficiency, very low cost. And so we use copper as much as we can on scale up, but on scale out, where the data centers are now the size of the stadium, we're going to need something much long distance running. And that's just where silicon photonics comes in. The challenge of silicon photonics has been that the transceivers consume a lot of energy. To go from electrical to photonic has to go through a SerDes, go through a transceiver and a SerDes, several SerDes. Okay, so first of all, we're announcing NVIDIA's first co-packaged option silicon photonic system. It is the world's first 1.6 terabit per second CPO. It is based on a technology called micro-ring resonator modulator. It is completely built with this incredible process technology at TSMC that we've been working with for some time. And we partnered with just a giant ecosystem of technology providers to invent what I'm about to show you. This is really crazy technology, crazy technology. Now, the reason why we decided to invest in MRM is so that we could prepare ourselves using MRM's incredible density and power, better density and power compared to Mach Zehnder, which is used for telecommunications when you drive from one data center to another data center in telecommunications, or even in the transceivers that we use Mach Zehnder, because the density requirement is not very high until now. And so if you look at these transceivers, this is an example of a transceiver. They did a very good job tangling this up for me. Oh, wow. Thank you. Oh, Mother of God. Okay. This is where you got to turn reasoning on. It's not as easy as you think. These are squirrely little things. All right, so this one right here, this is 30 watts, just so keep you remember, this is 30 watts. And if you buy it in high volume, it's $1,000. This is a plug. On this side is electrical. On this side is optical. Okay, so optics come in through the yellow. You plug this into a switch. It's electrical on this side. There's transceivers, lasers, and it's a technology called Mach Zehnder, and incredible. And so we use this to go from the GPU to the switch to the next switch, and then the next switch down, and the next switch down to the GPU, for example. And so each one of these, if we had 100,000 GPUs, we would have 100,000 of this side, and then another, 100,000, which connects the switch to the switch, and then on the other side, I'll attribute that to the other NIC. If we had 250,000, we'll add another layer of switches, and so each GPU, every GPU, 250,000, every GPU would have 6 transceivers. Every GPU would have 6 of these plugs, and these 6 plugs would add 180 watts per GPU, 180 watts per GPU, and $6,000 per GPU, okay? And so the question is, how do we scale up now to millions of GPUs? Because if we had 1 million GPUs, multiplied by 6, right, it would be 6 million transceivers times 30 watts, 180 megawatts of transceivers. They didn't do any math, they just moved signals around. And so the question is, how could we afford, and as I mentioned earlier, energy is our most important commodity. Everything is related ultimately to energy. So this is going to limit our revenues, our customers' revenues, by subtracting out 180 megawatts of power. And so this is the amazing thing that we did. We invented the world's first MRM micromirror, and this is what it looks like. There's a little waveguide. You see that on that waveguide goes to a ring. That ring resonates, and it controls the amount of reflectivity of the waveguide as it goes around, and limits and modulates the energy, the amount of light that goes through. And it shuts it off by absorbing it or pass it on. Okay, it turns the light, this direct continuous laser beam, into ones and zeros. And that's the miracle. And that technology is then, that photonic IC is stacked with the electronic IC, which is then stacked with a whole bunch of micro lenses, which is stacked with this thing called fiber array. These things are all manufactured using this technology at TSMC called, they call it COUP, and packaged using a 3D CoWoS technology, working with all of these technology providers, a whole bunch of them, the names I just showed you earlier. and it turns it into this incredible machine. So let's take a look at the video of it.